So the second approach we have is paging. This approach is actually let me select the page first. Yes. Okay, so this approach is different than uh, the previous approach of contiguous memory allocation, while this is a non-contiguous type of memory. Okay, as I have already told you, this is a non-contiguous type of memory. Okay, memory allocation scheme. Okay, memory allocation scheme. Okay, and so how this works? Now we know that non-continuous is a memory which can have the return the memory of one process. For example, this is a process. We have 3 locations, and the memory unit actually translate this unit somehow. We don't know until now how, but they somehow translate this and send the allocate the memory locations to this process. Then maybe can that allocation may be scattered. Okay, these 3 blocks can be scattered, and now we can have some mechanism here which can be used to access these locations again when they are occurred. So for here in memory management unit we have also something called page table. Now for suppose this is process 1 and we have maybe 0, 1, 2, right? So in the page table we already know that okay, P1 is stored in maybe 2, 5 and 7 locations. So 2, 5 and 7th location. Okay, 2, 5 and 7th location, the P1 is stored on these 3 locations. So whenever you want to access this, the page table, this is called the page table. The page table helps you to locate the uh, process inside the physical memory. Now this page table is actually the part of your main memory. Please keep this, remember that page table is actually the part of main memory. Okay, basically some portion of memory is allocated for maintaining this page table. Now when this page is coming from the CPU, we divide logical memory into block of the same size called pages. Now we have two things actually, the pages and frames. Now when it is stored over the uh, main memory, physical memory, we call them as a frame, but when it is being generated by CPU, we call them as a page. Okay, so one, it means that logical address of a page is mapped into physical address of a frame. Okay, so divide physical memory into the fixed size blocks called frames and divide logical memory into the blocks of the same size called pages. Now page and frame are actually of equal size. Why they are equal size? Because to minimize the internal fragmentation. Okay, to minimize the internal fragmentation. Okay, we have pages and frames of equal size, and uh, here is the example. In this example, I will show you that how actually this paging works here. So we have a page here, and we have some offset here. This is the page number. Okay, this is page number, and this is offset. And here we have frame number, and we have offset. Now, for suppose if we have some frame to locate here and this location, then how this page number and offset actually works. Now, for suppose if I have one page, let's say 0 page, and I have one page, so maybe here I have A, B, C, and D stored on the 0 location, on the 1 location, 2 location, and 3 location, right? And E, F, G, and H are stored on 0, 1, 2, 3 because every page has their own offset. Now this is the offset where the exact location of the memory record in the page. Now what happens that from the logical address, the page number is sent to the page table for the searching, right? Now it locates in the entire page table the location of the frame associated with this page number. Okay, so now for suppose we have got the location number 3, okay, or maybe 2, the location here is the location number 2 of this page. Okay, now maybe this is the page. Okay, this is the page. Now we got the location of frame that where it is actually stored. It is stored on the second location, but what is the offset? What is the offset is actually uh, for example, this is the page we are trying to see. Then for example, we want to access the second data, right? C. We want to access the C here, right? So this is offset. Now this offset is appended with this memory. Now 2 and 2. Okay, 2 and 2. So we will, this will help to map our physical address, the logical address into physical address by with the help of the frames number and the offset number. So frame number and the offset, maybe this is the offset. Okay, here we have A, and then we have B, and then we have C, and then we have D, right? So we need C here. So this is what the exact location of our record memory here, record data. Okay, in the paging model the same thing is shown here. Now for suppose we have page 0, page 1, page 2 and page 3. Now page 0 is actually stored on the location 1. Now this is page 0, page 1, page 2 and page 3. Now page 0 is stored on location 1, page 2 is stored on location 3 and page 4 is stored on location 1. Oh, sorry, yeah, and page 3 is stored on location 7. So this is how actually uh, the memory management using paging is done. Now in this type of memory management we have also wastage like fragmentation. Internal fragmentation is still there, right? For how? Because for example this in this example, if we say that every page is of size maybe 1k, right? 1k, 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 right? Every page is of size 1k, and every frame is also, because page and frame size is equal, now every frame size is also equal, right? 1k of all frames. Now for suppose if I have a program, okay, and it might be 2.3k in size. Now the last page would be written, when this would be written, 0.7k is actually wasted. So this is again the internal fragmentation, because the page size is 1k, and now we cannot actually write the remaining part of this portion of a page is actually wasted when we are writing the last bit of our process in the memory. So this wastage is again, we have internal fragmentation. It is again internal fragmentation. Okay, so this is the example which I have already given to you. For example, if we have uh, 0, 1, 2, 3, 3 pages or 4 pages, right? And then we have a page table associated with these pages. Okay, and then we have the locations of the page tables. Now, if you see that this is table number 2, which is stored on location 1. Okay, here, because it is starting from here. Maybe here we have something else. Okay, and this is 2. Okay, stored here, and this is 1, which is stored here, and this is 5, which is stored here, right? Okay, so the pages are stored on different locations, but they can be accessed randomly using the page table. So that's why this is actually random access, because we have some paging approach in this. We have a table in this. Now there are some issues with paging, and there are some disadvantages with paging approach. The first one is uh, the memory access time is larger, right? Because the page table is also part of the main memory, and the main memory itself is far away from the resources, right, from the CPU. So the access time is larger, right? It's large here, and we have to allocate two times. One from the we have to search through page table, and then from RAM, right, and then from the remaining part of the, okay. So we have some disadvantages of the paging. To overcome these disadvantages, we have again translation look-aside buffer, right? This translation look-aside buffer is again another table which is actually uh, uh, available very near to CPU. It is also called associated memory, right? This is associative memory, okay, associative memory. Now, associative memory is very near to CPU, and it is capable of multiple access. I'll show you in the picture here. Yeah. Here, for suppose CPU, in CPU we have now two tables in this scheme. The first one, we had already page table here, right? But now we have one extra table, that's the translation look-aside buffer table, right? This table is composed very near is actually maintained very near to CPU, so that the fast access can be done. Now, for example, if you go from here to this table, it might get less time, and also if you go to this table, then it might require some larger time, right? So because the distance is again larger here, right? This is the main memory. This is actually part of main memory, we know. So translation look-aside buffer. What is the property of this? The main property, the distinguished property of this translation look-aside buffer is that it is actually maintained in associative memory. Associative memory, okay. Now, associative memory is a type of memory which can be accessed for all locations simultaneously for all locations, for all of its locations. Okay, now this can be accessed for all locations. Now, for suppose if we have maybe 0 to 8 locations, then this is actually accessed for all locations. On the same time, this is searched through all locations. For example, if I'm looking for if, it may be number 5, but when it will take only the same time to search through all these, right? If it is found here. Now, for suppose here is a page which is required from the CPU, and CPU requests this page from the translation look-aside buffer table first, and if it is found in TLB, then that thing is called TLB hit. Okay, but if it is not found in TLB, then it is called TLB miss. If it is TLB hit, then the same thing will happen. This frame and this offset is combined to find the physical address of the required data, right? But if it is not found, then what happens that this is searched through the page table. The same way we have paging, and the same approach we have with paging. But there is something different, that when it is found with paging, it is actually not only sent to for the locating over the physical memory, but it is also sent to TLB. TLB now for updates, right? That because it was missed from here, so when it is being accessed, then this is actually also shared with the TLB for updating. Now, for TLB actually have one algorithm is uh, the recently utilized, right? It's least recently used, LRU. Okay, if all entries in TLB are full, then least recently used algorithm is used to replace uh, the old entries with the new entries. Okay, so for example, if at the start there is nothing, no entry in the TLB, but when the CPU tries to access different programs, then this TLB becomes populated, right? And when this TLB is full, then only uh, this when this TLB becomes full, then only this least recently used algorithm is used to overwrite the uh, existing old pages. Okay, and with the currently active pages. So inactive pages are removed from TLB, and active pages are actually added to the TLB. And lastly, we have swapping. Swapping is also another approach. Here from the baking store, we have actually here, for example, I will show you with some example. That for example, if we have P1 is running here, okay, P1 is already running here, and there's some time at some time unit of time, and this P1 has a priority of maybe 5, right? Priority of 5. While P2 has arrived lately, but it has priority of 1, means higher priority. Then what happens that this process is actually brought out of the main memory. We call it swap out, and the new process is actually pushed into the main memory, that is called swap in. Right. So this is the process of swapping. Okay, and this is actually used in two main algorithms. The first one is priority, when we have priority type of scheme. Okay, and the second one is uh, round robin, right? We have already seen that in round robin we have some quantum time. For example, if this process is for 50 unit of times, okay, and this process is maybe also 50 unit of time, okay, and the quantum is 10, then we will be only need, need 5 steps, right? 5 step in and 5 step out. But if this quantum is 2, then we'll be needing 25 step in, 25 step out. Okay, so we this is a very so that's why we say that the size of quantum should be larger, so that the processes should not swap, because swapping also require input and output operations, and it is not efficient for CPU utilization. It's not CPU efficient operation. Okay, so this is also one of the management uh, in the main memory. And the swapping is also done with the pages. Now same similarly, we have some pages in here which are already in your main memory. For suppose these pages belong to process A, capital A, and the high priority task from process B, some pages has arrived, and now they want to access the main memory. They may be the same portion. Then what happens that these pages are actually swap out. Okay, this is called, if we are dealing with the pages for swapping, then we call it page out. Okay, if we are dealing with some more data, then we call it swap out. And the new pages are actually ejected into the memory. So this is page in and this is page out, the same process, but the approach is different. There were dealing with entire process. Here we are dealing with the pages of a process. So this is the end of chapter, and I hope you, if you have any, I hope everything is clear to you. But if still we have some issue, we can discuss into the our into our live session. Thank you for your time.